In this video, we describe the Dirac delta distribution. This is a mathematical object. It's something like a function, but it's not exactly a function. It's sometimes called a generalized function or a distribution, but it's going to allow us to mathematically model what is called an impulse. An impulse is a large force that acts for a very short period of time. In some idealized sense, Dirac delta will represent that large force acting for a short period of time. After we talk about Dirac delta and where it comes from, we'll look at some properties of Dirac delta and we'll derive those properties. And then we will derive the Laplace transform of Dirac delta itself and the Laplace transform of a function multiplied by Dirac delta. So let's talk about impulses just to start. So an impulse is related to this idea of a large external force when I say large force, I mean large in magnitude, that acts for a very short period of time. So some examples are like a strike of lightning, of lightning. Wow, having trouble. Or pretty much anything being hit. So you can think of hitting a baseball, a golf ball. So whenever you're hitting a baseball or hitting a golf ball, what you see is that you have no force acting on that baseball or golf ball, and then suddenly you have a lot of force acting for a very short period of time, and then there's no force acting on it again as after that ball hits the club or hits the baseball bat. All of these are examples of impulses. This idea of a large force acting for a short period of time can be modeled by a function. Now, this is not Dirac delta itself, but we'll call it delta sub A, evaluated at t minus t naught. And this will have this value. It's going to be 0 outside of a particular interval. And then inside of a particular interval, it's going to be 1 over 2 times A. So we're going to make that 1 over 2 times A for all t values on an interval that's centered at t naught, but then we're going to add A to t naught and subtract A from t naught. If A is small, this represents that large force acting for a short period of time. So for example, let's say our t naught is right here. If A is, say, 1, we would go to t naught plus 1 from t naught minus 1, and we would think of this delta sub A function giving us a value of 1/2 on the interval from t naught minus 1 to t naught plus 1. And then it's 0 everywhere else. So in that case, the area under this curve would just be 2 times 1/2. Obviously, this is not to scale. 2 times 1/2 is obviously 1. But then let's think about what would happen if we shrink A, so that rather than having maybe a large force acting for 2 seconds with a magnitude of 1/2, maybe we have a force acting for 1 second. Now, 1 second is also centered at t naught. So we go from t naught minus 1/2 to t naught plus 1/2. In that case, we just looked at delta sub 1 of t minus t naught. Let me write this down first. It's going to be 0 outside of this interval, and then it's going to be 1 over 2 for t between t naught minus 1 and t naught plus 1. Then we're saying, okay, let's shrink a. Now, if a is 1/2, we're going to go backward 1/2 and forward 1/2 from this. And if a is 1/2, we're going to have 1/2 times 2, which is 1. 1 divided by 1 is 1 on this interval. So this function kind of looks like this. The area under this curve, well, is 1 unit by 1 unit. So that area is 1. The area under this curve was 2 units by 1/2 of a unit. So that area was 1. Let's shrink a again. Let's go to 1/4. 1/4 times 2 is 2/4, so that's going to be 1 divided by 1/2, which is 2. This is t naught minus 1/4, and this is t naught plus 1/4. And again, it's not to scale. But the area under this curve is the distance from negative 1/4, or t naught minus 1/4 to t naught plus 1/4. Well, that's a 1/4 plus 1/4 is 1/2. So we're going to take 1/2 and we're going to multiply it by 2. So that means that area is 1. I claim that all of these areas are 1. So if I were looking at the integral from negative infinity to infinity of this function, delta sub a of t minus t naught, well, it's only equal to something that's non-zero on the interval from t naught minus a to t naught plus a. The rest of the time it's 0. So this is really the same as the integral from t naught minus a to t naught plus a of 1 over 2a. And if I'm integrating that with respect to t, 1 over 2a is just a constant, so I just get 1 over 2a times t. And then when we evaluate from t naught minus a to t naught plus a, we get this. We have t naught plus a minus t naught minus a. And if we distribute that negative, we get that. The t naughts reduce, and then you just have 1 over 2a times 2a, which is, of course, 1. So this function has an area under the curve of 1, no matter what a is. But in some limiting sense, if we're thinking of a force acting for a very short period of time, of course, it's going to have to act over some time interval. It could be a time interval like this, or it could be a time interval like this, or a time interval like this. In the limit, as a approaches 0, what we would end up with here is a function that's 0 all the time, but then as a approaches 0, that the width of that interval is going to approach 0 as well. So we're going to have basically t equal to t naught in a limiting sense, of course. And what would happen to the function value there is that it would go to infinity. As a approaches 0, and we're assuming that a is positive here, as a approaches 0 from the right, from values that are slightly larger than 0, so we have a tiny positive number here, we're going to infinity. So we have something that's like a function, but it's not a function. It's 0 all the time and almost infinite at a point. But you can see that we can't have a function that's equal to infinity at a point t equals t naught. But that's what Dirac delta does. Like that's how we're modeling this situation. If Dirac delta is a function that is the limit of this function, or is the functional, we call it the functional or the generalized function. It's the limit of this function as a approaches 0. Sometimes people will call this the Dirac delta function. I prefer to call it just Dirac delta or the Dirac delta distribution or the Dirac delta generalized function. It has these properties. Dirac delta is the limit as a approaches 0 of that function delta sub a that I was just talking about earlier. And Dirac delta is equal to 0 for all t not equal to t naught. At t equals t naught, we would say it equals infinity, but that doesn't really make any sense. So, but in some limiting sense, it's almost like we have infinite amount of force acting at a single point in time, which is of course not possible, but it's an idealization of that situation. And we will say that the area under the curve for Dirac delta from negative infinity to infinity is equal to 1, because we are thinking of this as the area under the curve of this function. So as a approaches 0, the area under this curve is always equal to 1. It doesn't matter what a is. For any non-zero value of a, the value of this integral of delta sub a at t minus t naught is always equal to 1. And so because we're thinking of Dirac delta as the limit of this, well, it doesn't matter what a is. We would still have 1 over 2a times 2a, and those will reduce every time, and we're going to get 1, even as a approaches 0. So Dirac delta has this property, and it has this property, and it's kind of like this. But it's not, right? It can't be. It can't be like this and be like a function. Like it's like 0, 0, and then it's like sort of infinite at a point, kind of. It's a little strange, but that is Dirac delta. If you're interested in this, you should look up what's called the theory of generalized functions or the theory of distributions. I believe I learned about this in functional analysis. My functional analysis professor tells me that we didn't talk about this in functional analysis, but I'm pretty sure that I learned most of what I learned about Dirac delta from that professor. And I'm pretty sure he mentioned it, at least as an aside, in functional analysis one day, and I thought that was pretty cool. So yeah, this is our mathematical model, our idealized mathematical model for a force that acts at one point in time, and it's a huge force. It's a lot of force, like hitting a baseball with a baseball bat or hitting a golf ball with a golf club. You can think of that time period when you are actually hitting that ball as being very short or as being a single moment in time. And it's like you have no force acting on the ball, and then you have a lot of force at that point. So that's what Dirac delta is in some sense. Okay, so let's talk about how that relates to this integral. We talked about the area under the curve here, this integral from negative infinity to infinity of this being the same as the integral from negative infinity to infinity of this, this delta sub a function. Well, let's think about how that would work if we took our Dirac delta function and we multiplied it by f of t. Now, this is not really a proof. This is sort of proofy. just suggests that some of these facts that I'm going to give you are true. In order to prove everything, we'd probably need a little bit more background. So we'll say that this is the same as the integral from negative infinity to infinity of f of t times the limit as a approaches 0 from the right of these delta sub a functions. And let's assume that we can pull that limit outside of our integral here. Now remember how this function works. Delta sub a is 1 over 2a on the interval from t naught minus a to t naught plus a. And then it's 0 otherwise. So this integral from negative infinity to infinity really reduces to an integral from negative, or from t naught minus a to t naught plus a, because otherwise we're just taking this function f of t and we're multiplying it by 0. So with that in mind, we'll take this and we'll write this as the limit as a approaches 0 from the right of the integral from t naught minus a to t naught plus a of f of t times this delta sub a function, which has the value of 1 over 2a on that interval. Well, if we're integrating with respect to t, we can pull the 1 over 2a out. Now, by the mean value theorem for integrals, this is actually equal to the average value of f on this interval from negative, or from t naught minus a to t naught plus a, times 2a for some value of t in that interval. That's what the mean value theorem for integrals says. So let me just help you visualize that a little bit. Let's say that this is t naught minus a to t naught plus a. And I've got a function here. Here's f of t on that interval. Well, this area under the curve is represented by the integral from t naught minus a to t naught plus a of f of t dt. Well, that's going to be equal to the average value of this function on this interval. And that average value is a value of f for at least one value of t in the interval. And that is being multiplied by the width of the interval. So this is sort of a length times width thing, where the height of that rectangle is that f average. And then the width is this piece right here. So this distance is 2a. I hope that makes sense. Here's my height and there's my width. I guess I should be using length and width or something like that, but I hope you get the idea. It's just this dimension by this dimension, and that height is the value of the function that is necessary so that this times this equals that area under the curve. Well, the mean value theorem for integrals just says that there is some value t, at least one value t on the interval from t naught minus a to t naught plus a, where f will take on that average value. So when we are over here, I know that this is equal to this. This part can be written as 2 times a times f of t star, where t star is the particular value of t on the interval from t naught minus a to t naught plus a, where f takes on the average value. So if we do that, what we get is this. The limit as a approaches 0 of 1 over 2a times 2a times f of t star. And the 2a's reduce. And so what you end up with is the limit as a approaches 0 of f of t star. Now, since that doesn't depend on a at all, what we're going to get there is just f of t star. But as a is approaching 0, this interval around t naught is getting smaller and smaller. The interval is just getting closer and closer and closer to the actual value of t naught itself. So this t naught, or this t star, must actually be t naught. It has to be, because t naught is the only value that we're guaranteed to have in that interval as a approaches 0 from the right. So I hope that that makes sense. This fact is coming from the mean value theorem for integrals, which just says that there is some value of t naught where this function f takes on its average value. There's some value t naught on the interval from t naught minus a to t naught plus a, where f will be equal to the average value of f over that interval. And if we're shrinking that interval, so a is approaching 0, well then that t naught must actually, or that t star, excuse me, must actually be equal to the t naught. So that's another fact that we have just kind of proven. It's sort of proofy again. It's not, there's some fine print missing. Hopefully that suggests that this is true. The integral from negative infinity to infinity of f of t times Dirac delta at t minus t naught is equal to f of t naught. Sometimes Dirac delta at t minus t naught is called the sifting function or a sifting function, because what it does is when it acts on another function f of t and it acts on another function f of t like this, it gives you the value of f of t at t naught. So we're thinking of this as like a function, kind of a function. It's a functional, a generalized function that's 0 everywhere except for at t naught, and then somehow it's infinite. But if you take that and you multiply by a function and you integrate from negative infinity to infinity, the result is f of t naught. Again, this Dirac delta is called a functional or a generalized function or a distribution. And it's kind of like a function, but it's a little different. It acts on a different function. And when it acts on this function, it doesn't give you another function back like our operators and transforms do, or transformations do. It's actually acting on a function and giving you a real or complex number. So its domain, if you will, is a set of functions. And its range, the outputs are real or complex numbers. Now, it's been a little while since I've looked at this material myself, so please correct me if I'm wrong. It's been a few years since I've added this piece about functionals and generalized functions and distributions to my notes over Dirac delta. Okay, so what do we know about Dirac delta so far? It can be used to model an impulse. So that's a large force or a force of large magnitude acting for a very short period of time. And if we are thinking of that short period of time being a single instant in time, that is represented by direct delta. We said that delta at t minus t naught is equal to 0 for t not equal to t naught. And at t naught, I'm going to put this in quotes. That's why it's not a function. It's sort of equal to infinity at t equals t naught. And I can even say it equals infinity. I'll say it's sort of equal to infinity. It's just different. It's not really a function. But it's very useful because this situation where we have a large force acting for an instant in time, it occurs in reality quite often. So we've got this sort of expression in quotes, and we have the integral from negative infinity to infinity of direct delta at t minus t naught is defined to be this integral from negative infinity to infinity of delta sub a at t minus t naught, and that was always equal to 1. And if we take that direct delta and we multiply it by a function of t, what this ends up giving us is the function of t back, but it gives us that function evaluated at t equals t naught. So it gives us a single value. Okay, so now let's look at the Laplace transform of direct delta. I bet you can guess what it is. So direct delta, or the Laplace transform of delta evaluated at t minus t naught, is the integral from 0 to infinity of e to the negative st. And our input function here is direct delta at t minus t naught. But as I just mentioned, it's a shifting function. As long as t naught is greater than 0, this is going to give us this function evaluated at t naught. So we're going to get e to the negative s times t naught. And this is for t naught. I was going to say greater than 0. Should I say greater than 0? If t naught is equal to 0, will this work? And we would get 1 here. Yeah, I guess that would be fine. If t naught was equal to 0, we could get 1. Okay, and then we would do the same thing here if we're taking direct delta and we're multiplying it by a function f of t. And we want the Laplace transform of that. You have e to the negative s times, or st times f of t times direct delta at t minus t naught. And then again, this is a shifting function. What this does, when you take a function and you multiply it by direct delta at t minus t naught, it gives you the value of that function back at t equals t naught. So what we get over here is f evaluated at t naught times e to the negative s times t naught. And this is provided that t naught is greater than or equal to 0. So we don't actually use this piece, we just use those two pieces at the ends. And it's actually very easy in practice to compute those. And of course, if you're going from here to here, you will get a delta function back. So the inverse transform of e to the negative s times t naught is direct delta at t minus t naught. And the inverse Laplace transform of, well, actually, that's just going to be a constant times e to the negative s times t naught. So we won't worry about that in that case. Not actually going to be able to get f back if we just have f of t naught. It's just a number. So we wouldn't be able to recover f. Okay, let's apply that just to a couple of delta functions, just so that you can see how easy it is. Let's say you want to compute the Laplace transform of E or of Dirac delta at t minus pi. You're just pattern matching. This is delta at t minus t naught, so t naught is equal to pi. So we get e to the negative s times t naught. So you have e to the negative pi s. Or let's say you've got the Laplace transform of t cubed times Dirac delta at t minus 3. Well, actually, let me use a different number. Let's say t minus 4. Well, then in this case, my f of t is just t cubed, and then I'm multiplying by Dirac delta at t minus t naught. This is a shifting function, so what this does is it evaluates this function at t equals 4. So we're going to have 4 cubed, and then it multiplies it by e to the negative s times t naught. Matching the patterns, we see that t naught must be equal to 4. So we get that. So we end up with 4 cubed, which is 64 times e to the negative 4s. Easy, very easy. Now, if you're saying to yourself, where have I seen something like this before? Remember this? When we took the Laplace transform of f of t minus a times h of t minus a, we said that that was e to the negative as times the Laplace transform of f of t. And that's e to the negative as times f of s. If you are thinking of this whenever you see this, that's a good thing. Because they are related. This Heaviside function and this delta function are related. The Heaviside function allows us to write piecewise functions in a compact form and then compute the Laplace transforms of them. So the Heaviside function is allowing us to solve differential equations where the right-hand side of the differential equation is a discontinuous function. So we're saying to ourselves, well, what function y of t can I differentiate twice and multiply by these coefficient functions and add them together, and when I'm done, the result will be this piecewise continuous function on the right-hand side. That's our piecewise continuous forcing function. Well, the Heaviside function allowed us to deal with that. Now we're talking about the same type of thing, but instead of having a piecewise continuous function, we've got a function that is representing a very large amount of magnitude at a particular point in time, a large magnitude force at a particular point in time. So it's like an infinite amount of force at t equals pi, or an infinite amount of force at t equals 4 here. It's very strange, very different, but it works. And we are able to solve differential equations that represent that situation where you would have a large force acting on the system for a very small period of time using Dirac delta. Now, the Heaviside function at t minus a looks like this. It's 0 until you get to a, and then at a it jumps up to 1. Now, if we were to take the derivative of this, what I would expect to get is 0, right? I would say it's 0 here, and then it's 0 here. But then at this jump discontinuity, a function that's not continuous is not differentiable. So the derivative does not exist at t equals a. But in some other sense, in some world of generalized distributions, some world of generalized functions, it's possible to take derivatives of things that look like this, and then you get things that look like this. Or in this case, if that's an a, that's going to be Dirac delta at t minus a. So it's like wherever we have a jump discontinuity, we would have a delta function when we compute its derivative, which is very strange because everything that you've learned about derivatives so far contradicts that. We're told that if a function is not continuous, it can't be differentiable. And if a function is differentiable, it has to be continuous. But now we're talking about these functions and we're saying, well, what would the derivative of this unit step function be? We're like, in some sense, it's kind of like this. And if I say in some sense and you say in what sense, that's a good question for another class and even another teacher. I'm not an expert at this stuff anymore. It's been a long time since I've looked at generalized functions and distributions. But if you're interested, again, you want to look up the theory of generalized functions or theory of distributions, and you can learn more about that there. Okay, I will see you in the next video where we will solve differential equations that feature Dirac delta on the right-hand side as part of our forcing functions, either constants times Dirac delta or functions of t times Dirac delta. With these rules for the Laplace transform, we can see that we're going to get something that looks like this, and that's going to be common. Now, when you are solving a differential equation and you had a Dirac delta on the right-hand side to begin with, it makes sense that whenever you solve that differential equation, eventually you're going to end up with a heaviside function because you're going to end up with an e to the negative as times some function of s, and then you're going to try to get that function back. When you're taking inverse transforms of something that looks like this, you end up here. So Dirac delta and the heaviside function are very intimately related to each other, and they're related to each other in this sense that in some sense, Dirac delta is like a derivative of the heaviside function. So see you next time. We'll solve some differential equations featuring these guys.